All right, so these are the notes for 5.2. A lot of them are already written out. When we get to some of the examples on the back, though, I will write them out with you guys. So this is natural log and integration. It's not too long. It's only front and back. Most of it is examples. So remember that the derivative of ln is 1 over x. So therefore the integral, which is the opposite of the derivative, the integral of 1 over u would be ln of u plus c, as long as you have that du there. Or vice versa, again, the integral of u prime over u du is ln of u plus c. So we'll do some examples to make that make a little more sense in just a minute. Here are some guidelines for integration. So at any point, if I'm going too fast in the video, just pause it. Obviously, I'm going to talk faster than you can write probably. So at any point, just pause it, and then you can copy down what you need to write before we go on. So it says memorize the list of integration formulas. It's on page 388. You should know most of them already, but there are a few that we are still learning that you may or may not know yet. I also have 12 of them down here below, the integration formulas we've learned so far, so we're also going to write those down in just a minute. So you should memorize those, know them like the back of your hand, make flashcards for them. I would do that now as we lead up to the AP test, just so that you guys can start studying them now so you won't even blank on it when we get to the AP test. Number 2, find or recognize an integration formula that resembles all or part of the integrand, and use u substitution if necessary. This is kind of a trial and error part of the integration things, so you have to kind of look to see if there's something that looks familiar that could possibly be one of our integration formulas and try and make it fit one of the rules that we know, and then use u substitution in order to make the rest of it work. And then number 3, if u substitution does not work, try altering or manipulating the integrand by using either a trig identity, multiplying both the top and bottom by a number, or adding or subtracting the same number on the numerator. And we'll do some examples of those in just a minute. So here are 12 integration formulas we have learned so far. I want you guys to copy all of those down. I won't go through and read them all, but definitely pause the video and copy all of them down so you have them all in one place. These are the ones we've learned so far. These 4 over here are new. The ones that I've highlighted, those are new, so you probably don't know those yet, but you definitely should. So make sure you write them down as well. And those are, some of the ones you need to memorize. So, if you have all those written down, we'll move on to some examples. So let me zoom into example number 1. Now, like I said, some of these examples are written down already. We'll do some of them together, though, so that you can kind of see it as we go through. So for example 1, we have the integral of 1 over x minus 5. So hopefully you recognize that that kind of looks like 1 over some number u, or some function u, I should say. So we can use u substitution and set u equal to x minus 5. That's the inside function. And the derivative of x minus 5 is just dx, 1 dx. So I see that piece matches up with that piece. I can plug in u for x minus 5, and I have 1 over u du. So the integral of 1 over u du is just ln of the absolute value of u plus c. And if you plug u back in, you get ln of x minus 5, absolute value of x minus 5 plus c. So that one's not too bad. Simple u substitution. Let's look at number 2. Again, hopefully you recognize that this is something over 3 minus x cubed. So, and one thing that you can kind of look for that might help you as like another guideline to help you is that always look for powers that are 1 less. So like if this is x cubed, this is x squared. So obviously if we're looking for u substitution, the one with the x cubed must be our u, because when you take the derivative of x cubed, you get x squared. So that's probably where we're going to get our derivative from, is that term up there. So if you make u equal to 3 minus x cubed, we have that over here. The derivative of this is negative 3x squared dx. So I see an x squared and I see a dx. I do not see a negative 3 though, so I'm going to divide by negative 3 on both sides to get negative 1/3 du equals x squared dx. And I will use this as my substitution for the du, and I'll pull out that negative 1/3 because I don't need it. And then I have 1 over u du, because u was equal to the bottom of that. And the integral of 1 over u is ln of the absolute value of u plus c. So we have negative 1/3 ln of the absolute value of 3 minus x cubed plus c. Alright, so you can pause the video, make sure we have all that copied down, make sure you kind of go through it and understand it step by step. I started this one on the back yet, I have not finished it yet though, so we'll be working on this one together. So, for number 3, we have u equals 9 minus x squared. If you take the derivative of 9 minus x squared, you get negative 2x dx. So I see that there is no negative 2 in my equation. I just have the x dx, so I divide both sides by negative 2, and I get negative 1/2 du equals x dx. So when I use that and plug that into my u substitution, if I can zoom into this a little bit, oh, that's way too far. There we go. I can pull out the negative 1/2 out front, so I have negative 1/2 times the integral. The x dx is my du, so I'll have 1 over the square root of u du. And this is actually not the logarithmic integral, it's just one that we already know already. So this is actually negative 1/2 times the integral of u to the negative 1/2 du, which if you bump up that power by 1, the reason, by the way, that 1 over x, you can't bump it up by 1, because if you do 1 over x, that's x to the negative first power. If you bump negative 1 up by 1, that's 0, and so that wouldn't make sense. That's why the integral of 1 over x is ln. But here, u to the negative 1/2, we can bump that 1 up by 1. So we get u to the positive 1/2 divided by 1/2 plus c. Or that should be a 2, sorry, not a u. So if I multiply the 2 up to the top, since I don't like fractions in the bottom, the negative 1/2 would cancel with that too. So I just have negative, and then if I plug u back in, square root actually, negative square root of u, which is 9 minus x squared plus c. Alright, if we look over here, try and make this a little better. There we go, it's not as blurry anymore. So now for this one, again I said to look for powers of x. So this is x squared, this is x. So if anything, this one down here is going to have to be my u. So let's make u equal to x squared plus 6x plus 7. And du, the derivative of that, is equal to 2x plus 6 dx. Let's see, I see x plus 3, and here's 2x plus 6. So if we divide this by 2 and divide this by 2, I would get 1/2 du is equal to x plus 3 dx, which is perfect because that's what I have up here. So I have x plus 3 dx. That 1/2 is the only thing I had to get rid of. So I have 1/2 integral of 1 over u du. So that would be 1/2, the integral of 1 over u is ln of the absolute value of u plus c. So that would be 1/2 times ln of the absolute value of u, which is x squared plus 6x plus 7 plus c. You could, if you wanted to, properties of logarithms say that you could take this 1/2 and put it back up top, up here, and take the square root of this, since it's the property of a logarithm to do that. So that works if you'd like to do that. It only works, by the way, or if it's 1/2 or an even number, like 1 over an even number, because of the absolute value. It would get rid of the negatives if it was even, so that's why. All right, let's look at number 5. All right, on this one, remember that we always want our u to be our inside function, so if we make u equal to x minus 1, by the way, you might be tempted to multiply up here, but I would say always look for inside-outside functions first for u substitution, just because if you multiplied that up there, you might think that that was your u, but you wouldn't get a derivative that was cubed, so that wouldn't make any sense. Du here is just 1 dx. I still have this whole extra thing on top though, so remember, if I have extra x's up top, I just have to solve u for x. So x would equal u plus 1. It's a plus. So if I plug everything in, I have the integral, x is u plus 1, then x minus 2 would be u plus 1 minus 2, so u minus 1. Again, that was, if I plug in u plus 1 here to x, I get u plus 1 minus 2, and u plus 1 minus 2 is u minus 1. That's how I got that. And then this would be u cubed down here, du. So if I multiply out the top, I get u squared minus 1 over u cubed du. And I can split up that fraction into two separate fractions. So I have u squared over u cubed minus 1 over u cubed du. So the first integral simplifies to 1 over u. The second integral is minus u to the negative 3 du. So if I integrate that, I get ln of absolute value of u. The integral of negative u to the negative 3 is negative u to the negative 2 divided by negative 2 plus c. So my final answer is ln of the absolute value of x plus 1, because that's what u is. The negative negative cancels out, so that's plus 1/2. Well, I guess I could write this in the bottom since it's u to the negative 2. Plus 1 over 2 times u squared, so x minus 1 squared. Is that a minus then? My bad, this should be a minus here too. So ln of x minus 1 plus 1 over 2 times x minus 1 squared plus c. All right, number 6 is a little bit tricky in the way that you would do it. If you tried making u equal to the square root of 2x, you would notice that the square root of 2x, the derivative, actually just 2x, the derivative would just be 2, and then we have 1 over 1 plus the square root of u, and it just would get kind of confusing. So if you make u equal to the entire denominator, and you might need a little bit of room on this one, so maybe write a little bit smaller. If we take the derivative of that du, that would be 1 over, the derivative of 1 is just 0, the derivative of the square root of 2x, since that's 2x to the 1/2, it would be 1/2 times 2x to the negative 1/2, and 2x to the negative 1/2 is down here on the bottom. So that's the derivative of the outside, times the derivative of the inside would be times 2, so this 2 would cancel out with that 2. So du would equal 1 over the square root of 2x dx. Well, that's great and all, but there is no 1 over the square root of 2x over here. So we have to do a little bit more manipulating, and that's where it gets just a little bit tricky. I do notice that I have, I could get rid of this 1 over the square root of 2x over to this side. So if I multiply the square root of 2x on both sides, I have the square root of 2x du equals dx. But remember, you're not allowed to pull a variable outside of the integral, so it's not like I can just say that this is going to be pulled out of the integral. I actually have to find out what this equals. So again, notice up here I have a square root of 2x in my u. So if I actually solve this, I can say that the square root of 2x is equal to u minus 1. So then this is equal to u minus 1 du, which is equal to dx. So if I plug those into my integral, I have the integral of dx is equal to u minus 1 du, and then on the bottom of this I have the 1 plus the square root of 2x, which is equal to u. And that looks much, much simpler to solve now. So I can split this up into two fractions. I have the integral of u over u minus the integral of 1 over u du. So that would be the integral of 1 minus 1 over u du, which is equal to u minus ln of the absolute value of u plus c. And if I plug all those u's back in, u is equal to 1 plus the square root of 2x minus ln of the absolute value of 1 plus the square root of 2x plus c. And then a lot of times what the AP Calculus, because technically this is a correct answer, but the AP Calculus exam and tests in this chapter recognize that 1 is a constant, so they just combine it with this constant over here. So this is just going to be the square root of 2x minus ln of the absolute value of 1 plus the square root of 2x plus c. All right, good. That was number 6. All right, on this one, let's make u equal, here, I'll write it over here, so we are running out of room. We'll make u equal to 1 plus cosine of x, and therefore du is equal to negative sine of x. I see a sine of x there, I don't see a negative though, so I'm going to move the negative over to the other side. So negative du equals sine of x dx. So if I do some replacing in this, I have the integral of sine of x dx is just negative du, so I guess I can bring that negative out now. And then 1 over u du. So this is equal to negative ln of the absolute value of u plus c. So negative ln of 1 plus cosine x plus c. Oops, absolute value. 1 plus, there we go. All right, good. That was 7. Let's look at 8. Oh, by the way, before we go over to 8, on number 7 as well, you can, if you would like to, move the negative up to the top as a negative 1 exponent, and then the 1 plus cosine of x would actually be on the bottom. So it would be ln of 1 over 1 plus cosine of x plus c. You don't have to write that now in your notes, but maybe just make a little note of it, because on the AP test, they could write the answer like that, and you need to be able to recognize that that is another way of writing the answer. All right, number 8. All right. We're actually going to skip number 8 for right now. Just because it would take a little too much time for the purposes of this video. So let's look at number 9. It says, solve the differential equation. So we're going to work backwards. We were taking derivatives before, still now we're taking integrals. So to solve this differential equation means to take it backwards and go back to the original function r to figure out what r is. So how we do that is we move the dt over to the other side of the equation so that we can set up the integral. So hopefully I don't go off the page here, but we have dr equals secant squared t over tangent t plus 1 dt. And remember, we said to always look for something that fits one of the integral rules. So you'll know that the derivative of tangent is secant squared. So that's probably the derivative of the inside. So I'm guessing this is going to be my u down here. So u equals tangent t plus 1. du equals secant squared t dt, which is what I have here, secant squared t dt. So dr is therefore equal to 1 over u du. So if I integrate both sides like this, I get that r is equal to ln of the absolute value of u plus c. And if I plug my u back in, I get that r is equal to ln of the absolute value of tangent t plus 1 plus c. And they want me to solve it at this specific point at pi comma 4. So I'm going to plug in pi for t and I'm plugging 4 for r. So if I let r equal 4, that means that ln of tangent of pi plus 1 equal plus c, sorry, or my c is what I'm solving for in this case. So tangent of pi, well, pi is the point. If I can, just want to make sure I have enough room. Here, I'll zoom out just a little bit so I don't cut you guys off. If you look here, pi is over here, and this is the point negative 1 comma 0. So tangent is sine over cosine, so that would be 0 over negative 1, which is equal to 0. So this is 0 plus 1, so that's ln of 1. So this says 4 equals ln of 1 plus c. Well, we know that ln of 1 is equal to 0, so that means that c must equal 4. And if c equals 4, we can plug it back into our original equation, and we can say that, excuse me, r equals ln of the absolute value of tangent t plus 1 plus 4. Just like that, now that we know our constant. Good, so that's solving a differential equation. You just have to move the dt over to the other side and then integrate as normal, and then at the very end you can figure out what your c is. All right, let's look at number 10. I'll try and zoom back in on this one. So this is actually a definite integral because it has limits on the integral, as you can definitely see here. So if we're trying to do this, I'm going to make u equal to ln of x. Now you may be asking why I'm not making u equal to x ln of x. And that's because, remember that the derivative of ln of x is 1 over x. So I actually want to keep that there as part of my derivative. So du is equal to 1 over x dx. And I have that here, 1 over x dx. That's perfect. So if I plug everything in, I get the integral from e to e squared of 1 over u du. So the integral of 1 over u is ln of absolute value of u from e to e squared. So if I plug in e squared, I get ln of e squared minus ln of e. Well, ln of e squared is just 2, and ln of e is just 1, so that's 2 minus 1. My bad, sorry. Couple things. Number 1, you can't even see this. Number 2, I made a mistake. Do you remember or recall, and I remember a lot of you guys asked me this right before we took the test, when you change it to u substitution, if you're not going to plug in what u equals back into the function, you actually have to change the limits of integration. So let's do that really quick. When x equals e and when x equals e squared, let's figure out what u would equal. If x equals e, ln of e is equal to 1. If x equals e squared, ln of e squared is equal to 2. So let's fix that right here. My bad. So this is going to be from 1 to 2, from 1 to 2. So ln of 2 minus ln of 1. That's much better. So this would equal ln of 2 minus 0, which is just ln of 2. My bad, didn't mean to mess you guys up on that change of limits. Alright, and the very last one that we're going to look at for today is number 11. So it says find f prime of x. So this is actually one of those easy ones again, so we saved the easiest for last. So remember with f prime of x, if you have f of x and they want you to find the derivative, this is back to that day of really easy stuff where you just plug in the limits. Since we're plugging in an x, it was in that fundamental theorem of calculus section from chapter 4. You just plug it in for the variable and then multiply it times the derivative. So, well, for example, let me show you the actual integration and then I'll show you the shortcut way. So if I actually integrate this, I have the integration of 1 over t, to be ln of t from 1 to x squared. So if I plug in x squared to that, I get ln of x squared minus ln of 1, which was just ln of 1 is just 0, so this is just ln of x squared. So that would be the integral, all right? F of x equals the integral. That would be f of x. So this is equal to f of x. And then if I said find the derivative of f of x, the derivative of this is equal to 1 over x squared times the derivative of the inside, so times 2x, which equals 2x over x squared, which equals 2 over x. So that's f prime of x. Now again, with the shortcut way, if you had just come back up here to the top and plugged in x squared right here into 1 over x squared and then multiplied it times the derivative of x squared, which is this, that's what we would have gotten originally. And that's again because we're taking the derivative of an integral. They cancel each other out. You just plug it in and multiply it times the derivative of this. And again, if you're confused about where I'm getting that from, go back and look at our notes from chapter 4 on the second fundamental theorem of calculus, and it's in that section. All right, that's it for today. You guys will work on the homework during class tomorrow, and well, you can go over it on Thursday when I get back. All right, thank you very much.